today we're going to continue in chapter 1 topics, and these are found in section 1.4 through 1.5, and we might touch a little bit on some stuff in chapter 1.3. And the main point for today's first part of our video is Dalton's atomic theory. We discussed a little bit about the atom in our last lecture, and the atom, or atomos, was first proposed by the ancient Greeks, and there was a period of time, nearly 2,000 years, when that idea of the particulate matter of the particulate nature of matter as being an atom wasn't really accepted in the scientific community until the 1700s, when science began testing and doing experimentation to support observations that were made. And a lot of these were conducted in some very simple laboratories. What we're going to show today is that Dalton's atomic theory is supported by 3 laws, scientific laws. This includes the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So before we break into Dalton's atomic theory, there are some terms that I think we should address, and that's theory and law. What's the difference between a scientific theory and a scientific law? You can stop the video if you want. Stop. Okay, going back. Let's think about what a law tells us. A scientific law tells us a little bit about how nature behaves under a certain set of conditions. If you've taken a physics class, you might recall Dalton's law, or Newton's law of motion. Force is equal to mass times acceleration. That's a scientific law. It simply tells us that if we have a certain mass of an object and it's moving with a certain acceleration, it exerts a certain force. It simply states how matter behaves under a certain set of conditions. It doesn't explain the observation. That's where theory comes in. Theories offer explanations to observations that we may make in a laboratory. And what we're going to show today is that Dalton is going to make some observations, and he's going to use some of the laws that were available at his time, and he's going to create what are called some postulates. And that's what we're going to look at today. The postulates, we're going to look at 4 postulates of Dalton's atomic theory. And one thing that's important about a theory, and we're going to get into this today when we discuss Dalton's atomic theory, is that theories can change over time with the use of more sophisticated instrumentation, more sophisticated techniques in science. And that's exactly what we're going to see when we start to discuss a little bit about Dalton's atomic theory. So we're going to list his postulates. So a postulate, that's basically a basis for your reasoning. So that's what a postulate is. Let's look at Dalton's atomic theory and his 4 postulates. His first postulate is that all matter is composed of small, indivisible particles called atoms. So matter is composed of small, indivisible and let's capitalize indivisible. Indivisible. Make sure I can spell it and underline it. Indivisible, not invisible. Indivisible. Indivisible atoms. So what does indivisible mean? It means we can't divide them into any smaller component. So what we're going to show, and what we do know, is that later, and as we're going to learn and study a little bit later today, atoms are divisible. We can divide them. We can find smaller components of subatomic particles of atoms. So this is a postulate of Dalton's atomic theory that later we learned is not necessarily true and we had to modify this definition. What we simply know today is that matter is composed of small atoms, and these atoms are divisible. They have subatomic particles. Three that we're going to learn about later are the electron, the neutron, and the proton. So that's the first postulate. Let's list Dalton's second postulate. Now, what Dalton believed at his time, elements, and this was the first listing of an element, elements are going to be a sample of matter composed of identical atoms. They have identical atoms. They share similar chemical properties. We'll say they have same chemical properties. And Dalton believed they had the same mass, same size. Atoms of different elements are going to be different. That's basically what we're going to show. Or another way of looking at it, elements have identical atoms for a particular element. Now, I want to discuss a little bit about the size, the mass issue, because again, we have to modify Dalton's atomic theory here, because atoms of a particular element don't all have the same mass. If you know why, you're a little ahead of the game. And the reason is, as we're going to learn later in this chapter, is due to the existence of what we call isotopes. And that is another fact that was discovered later in history. So at Dalton's time, we didn't know about isotopes. He didn't know about isotopes. So those are the first two postulates of Dalton's atomic theory. Let's move into the third and fourth postulate that we're going to look at. Let's get a lot of space here. The third postulate of Dalton's atomic theory. Compounds. Okay. He focused on compounds. Compounds are composed of two or more atoms of different elements and they do so in defined ratios, defined whole number ratios. And this third postulate is what's supported by two of the laws that we just discussed. And we'll get into a little more detail. This postulate is supported by the law of definite proportions and the law of multiple proportions. Both of which we'll further discuss in a few minutes after we finish our fourth postulate. Fourth postulate. And this postulate about compounds, still, there's no changes. We still abide by these. There's no real changes that we've made over the past 200 years. The fourth postulate, atoms of one element cannot be changed into an atom of a different element by a chemical reaction. Well, what happens during this is in a chemical reaction. Now, once again, this postulate, notice we focus on the word chemical reaction. However, in modern times, we can encourage nuclear reactions, and in a nuclear reaction, we can change the identity of atoms. So in this case, we're specifying a chemical reaction. And what happens during the course of a chemical reaction, we don't change identities of atoms, we simply rearrange them. And what we have to show in a chemical reaction is that the law of conservation of mass has to be observed. And that's the nature for a balanced chemical equation, a topic that we'll be covering a little bit later in this semester. So let's go and talk a little bit about, as I promised, the two laws that we were discussing here and how we can identify these. The law of definite proportions and the law of multiple proportions. Let's show examples of these so we understand more about those two laws and how they're related to how compounds are formed. And we'll leave the balancing of chemical equations to a little bit later in this semester. Let's look at these two laws that we have here, and let's show some examples of what we mean when we're discussing the formation of a compound and how it's related to the law of definite proportions and how it's also related to the law of multiple proportions. You need to be able to distinguish between these two laws. Let's look first at the law of definite proportions in the formation of a compound. And let's look at an example of a compound that we might be familiar with, ammonia. Ammonia has the chemical formula N, which is nitrogen, and H with the subscript 3 tells us that there are 3 hydrogens that are bonded to each nitrogen atom. And this makes up the molecule or the compound. Molecules will be discussed later also. This is the compound ammonia, NH3. And what this tells us is that wherever we collect this sample of ammonia, remember we discussed this when we were introducing pure substances, all samples of ammonia have 1 atom of nitrogen combined with 3 atoms of hydrogen. And this ratio is constant. For every sample of ammonia, there's 1 atom of nitrogen for every 3 atoms of hydrogen associated with it. And this is reflected in what we mean by the law of definite proportions. There's a definite proportional amount of nitrogen and hydrogen in every sample of ammonia that we can find. And that's one of the ways we can define a chemical compound. They have fixed ratios of atoms, regardless of where we collect that particular sample from. Let's look at the law of multiple proportions. How does it differ from the law of definite? Definite proportions tells us the ratio of atoms, the different atoms are fixed for a particular compound. Law of multiple proportions. Let's define the law of multiple proportions. Wording is important. Let's make sure we write down the exact definition. The law of multiple proportions. So let's read. I have this in my PowerPoint. Let's make sure we understand what this means. The the legal jargon. Okay, if we have if two different, and that's important, two different compounds are formed by the same two atoms, we'll say same two elements. Atoms, we'll put that in parentheses. They combine in different ratios. So let's read it and try to absorb what this is telling us. Two different compounds are formed by the same two atoms or elements. They combine in different ratios. Okay, let's think of an example to present what we mean by the law of multiple proportions. Now, we're familiar with water. We drink water. Water has the chemical formula H2O. The ratio of hydrogen to oxygen atoms, well, we have one oxygen atom for every two hydrogen atoms. Okay, so it's a 1-to-2 ratio. For every compound of H2O, one oxygen and two hydrogen. Let's think of another compound that forms from the same two elements, hydrogen and oxygen. There is another one we might be familiar with, hydrogen peroxide. As we were stating here, it's a different compound, but it's formed from the same two elements, hydrogen and oxygen. Hydrogen peroxide has the formula H2O2. In other words, for every two atoms of oxygen, there are going to be two atoms of hydrogen bound to them. So what we see is that in both cases, they're formed by the same two elements, but they're different compounds. What differs about them is the combining ratio of the different elements. Water, we can drink it. Hydrogen peroxide, do not drink it. It's not good for you. It'll make you sick. So that's an example of the law of multiple proportions. The law of definite proportions and the law of multiple proportions help us to understand better about how chemical compounds form. So Dalton's atomic theory, it opened up the door to more investigations later in the early 20th century and the later part of the 19th century. And as we said, what we're going to show in our next video, the next video that we're going to cover will involve chapter 1.6 through 1.7. Part 2, we're going to introduce 3 subatomic particles. And when I say subatomic particles, these are the particles that make up an atom. And there are 3 of them that we're going to be discussing. These include the electron, the proton, and the neutron. And that'll be discussed in the next part of this lecture. So Watch the next one.